Hello, my name is Mustafa and Gurbuz, and this is the motion of a falling object lab in Physics 2211. A brief overview of what I'll be going over in this lab is I'll have an introduction, surroundings, assumption, initial conditions, models, and sources of error. I'll also go over the details of my experiment, how I wrote the computational models using GlowScript, then I'll go over comparing all of the graph and answering what if or what does it mean. So, the introduction. The purpose of our lab is to observe the motion of an object after it's dropped from a certain height and then compare this with the different computational models, one which has gravity and one which has both gravity and the drag force on it, to see which one goes to terminal velocity. So some fundamental physics principles is Newton's second law, which is the acceleration of an object is directly proportional to the net force and inversely proportional to its mass, also known as F equals ma. The gravitational force, which is force directly proportional to the product of the masses and inversely proportional to the distance between them squared, which is also known as F equals gm1 m2 over r squared, as well as the drag force, which is generated by the relative velocity between the object and the fluid, commonly represented by 1/2 c rho a v squared. A preview of the main result of this lab is just that the predicted graph with just gravity showed that the ball fell faster than what the observed graph showed, but the graph with computational model with both gravity and drag gave very similar results to that of the observed graph. So the surroundings, assumption, conditions, models, and sources of error. So the system was the paper ball and the surroundings were the air around it, my hand, and gravity. Some assumptions I made in this lab was that I assumed that no errors were made during the plotting process using tracker as I plotted it manually, and that there were no outside forces acting on the paper ball that could have impacted our results. The model I used was a position in meters versus a time in seconds graph. Some initial conditions I set was that the ball started at the origin of the axes. Some sources of error that could possibly change this is that the paper ball wasn't completely spherical, therefore it didn't follow a straight path downward, possibly affecting the results. And because I had to plot the center of point of gravity, mass, these could further my tracker input results being incorrect. So the details of my experiment. I just dropped a paper ball from a certain height and recorded it falling. Started recording when the ball was starting to accelerate out of my hand. As you can see, the y graph over there isn't going at a constant velocity, so it took time to accelerate, constant velocity, and then slow down once it hit the ground. I put this video on tracker and then plotted the point of center of mass as best I could until the ball hit the ground. And then I compared the observed model of the graph with the calculated computational graphs, which will come later. So here's the glow script code for no drag. I just changed the ball position vector to having 0.8 in the y direction to account for the height of my releasing position. The b, which is what we're using to calculate drag in this scenario, is 0 because this is for code without drag. I changed the time to 0.576 seconds because that's how much time it took for the ball to when it dropped from my hand to hit the ground. Then I calculated net force by calculating gravity and drag separately and then combining them. And then I just made a velocity update formula and a position update formula to update the ball's position and velocity. So the glow script code with drag is very similar. It's just that b is equal to 2.4 instead of 0, taking into account the drag. So comparing all of these graphs, we can see that the no drag graph actually in the time given goes all the way down to negative 0.8 meters, which is much too far, whereas the drag and the observed model goes only until 0, meaning that the drag model accurately can represent the observed position model, but that the no drag model overestimates. So what if or what does it mean? What if the object was thrown downward manually? Would the terminal speed change? No, the terminal speed would stay the same regardless if the paper ball was dropped or thrown downwards. This is because terminal speed is reached when there's net force equals 0, and for net force to equal 0, the drag force has to equal the gravity force. So once that happens, it's going to have the same terminal speed. And what does it mean? Do any of the models represent terminal velocity? Yes. The model with both gravity and drag represented terminal velocity. It was very, very similar to the observed data. Thank you for listening.